cross-platform analysis of potentially harmful libraries on Android and iOS. So it's a joint work with Chinese Academy of Science and Indiana University. So I need a button to put to the next page. So, okay. Okay, here's the second page. So, yeah, so we all know that potentially harmful apps has been widely spread even in major markets such as Google Play and App Store. Here, we avoid using the term malware because it's sometimes hard to tell whether an app is malicious or not. Instead, we use the term potentially harmful app. It's a term Google uses for describing applications which pose a security risk to users or their data. We also found the sources of potentially harmful behavior often libraries, for example, in contaminated versions of library, backdoored at library. So, okay, thank you. So we want to make some research on these potentially harmful libraries, but it's very, very challenging, and it has never been done on iOS side. So mainly it's three reasons. The first one is a library found online is mostly its latest version. So usually in the latest version, we cannot find the malicious code on site, the potential harmful code on it. And if we want to find like other parts of code, so we need to collect the apps and extract the special version of the library from it. The second reason is on iOS side, the attempts to recover library from apps is non-trivial. It's different from Android side. We can easily get the package from its code, so and it's packed together. But on iOS side, it's mixed, so it's a little bit difficult to do it. The third reason is there's no public system existing for finding iOS potentially harmful app. And even if we have found some suspicious apps, so without such system, it's hard for verification. So can we design an approach that can first, on Android side, gather Android potentially harmful library with different versions, and on iOS side, recover iOS library and scan them efficiently? So this is our observation. We found a significant portion of third-party services to Apple users are also provided to Android users. The data is from source DNA. And in the top 38 iOS libraries, 95% of them have Android versions. So our idea is to use this Android versions library and do a grid map and to use this other information to map to iOS side and to check the potential harmful libraries on iOS side. In the end, we achieve our goal. We do a great cross-platform study on 1.3 million Android apps and 140,000 iOS apps. The study is in 4 steps. The first one is to collect Android apps and try to extract the library from it. The second one is to check the potentially harmful library from those libraries that we have found. The third one is to do this map to iOS side. And the last one is, remember, in Apple Store, it's different from Android Store. So it usually has strict vetting process. So the potentially harmful behavior found on Android side may not be exactly the same on iOS side. It may be removed. So we need to do this behavior correction and to verify that the potentially harmful behavior also existing on iOS side. So this is the first one. So we try to collect Android apps and do this cluster. We found a library is typically used as a whole package and also structured in a standard way. So we use a name and put all the packages having the same name together into a group. But sharing the same name does not mean that the package belongs to the same library. For example, names like A.A.B is a faceted version. So our idea is to cluster them and use this package similarity degree, PSD, based on Jakarta index. It's a ratio, actually. And it's a ratio of the number of shared methods and the number of shared methods between these two packages and the method of these two packages. Then we use this PSD to cluster libraries inside a group. And we get the threshold to use two training sets, 20 randomly select libraries that has no relation to each other, and 20 libraries together with their different versions. So we can get a threshold and do the cluster. From the cluster, each cluster is a library, and it contains several variations. We can get it. So in the end, we got 1.3 million Android apps. From it, we got 763 libraries with 4,912 variations. Then we need to check whether there's some potentially harmful libraries inside it. Remember, we try to use VirusTotal. Remember that VirusTotal only accepts apps. It's not a library. So our idea is to create a dummy app. This dummy app only includes a library. And we can use, in this way, use this dummy app for like target scan. If VirusTotal raises the flag to see that this dummy app has some problem, is potentially harmful, so that means the library that we put it into the dummy app is potentially harmful. So then, after we get this potentially harmful library, we can do this map. We map an Android potentially harmful library to its iOS counterpart and validate the potentially harmful code. However, to do this map is not an easy job, because there's a huge gap between the two platforms. Here is some example. The left side is Android version, and the right side is iOS version. So they achieve the same functionalities to play some media. But we found that it's different system, and use different frameworks and APIs. The left side uses start, and the right side uses object message send. And second thing is that they use different languages, like Java and whereas Objective-C. So it's also different. And the third thing is that they are different developers, individual developers to develop these two platform apps. So we find the program structures and logics are different. For example, here on the left side, you only use one method to achieve this functionality. But on the right side, it's split into two methods. Fortunately, we have found some common things. It's cross-platform environments. Like here, we find add wall play audio. It is a command sent from a remote server to this app, to this client app, and to let the app to do something to play the audio. So it's the same. It's easy to think that it's like protocols between a server and a client. So either Android version or iOS version will be designed according to this protocol. So we try to explore more cross-platform environments. For example, here, the formatted data shared by client and the server, and the resources is shared resources across platform, and the developers' information, unique information such as the email address. And we can find some more, like ciphertext code, program logs, certain formats, URL related, and the commands and the JS code. Then now we have found there are some shared strings or shared environments among between these two platforms. So next question is, how many shared strings can infer a library pair? So we do a test. We collect 20 pairs of libraries, including 126 pairs of classes. So we found when the number of matched cluster strings within a pair of classes goes above 8, the false detection rate becomes only 1%. So we use this as a threshold. The problem is it's like the coverage is only 40%. So we need to explore more and to find the library members. Still remember, this has two challenges. The methods are mixed together, and the class name cannot represent a library. It's not like the Android version. So our idea is to use a matched class as anchors and extend to more classes. Here, suppose class A is an anchor. If it calls like another class D, B, or inherent C, or refer D, so we think that B, C, D are also inside the same library. But the situation becomes complex if another class F calls A. Because a library usually supports functionalities to other code like the app. So it can support this interface to F. So we do not know whether F is inside the library or not. So our idea is to look back to the Android code and find if there is a similar class, F prime, that also calls A. And if another F prime has some shared strings with this F, we think that, okay, F is inside the library. Here, but E does not meet this constraint. So finally, we get this library and it removes E. So now we can do this potentially harmful behavior mapping with the Android library. It could be dropped from iOS part, just like we mentioned before. So our idea is to use the comma part and pack this comma part to a dummy app and submit to VoiceTotal. Then if VoiceTotal flags that there's a problem with this part, so we say that the iOS part that have the same behaviors are also potentially harmful. So we do this behavior mapping. So here we model a library behavior across platform. Usually, previously, people could use this API sequence. It's easy to use a dictionary for mapping. But on iOS and Android, it's difficult to do that. This is because they had two frameworks and two API sequences. So here we use this one, API category plus environments for this mapping. We also we manually do this dictionary, and we want to put it open on this website, appomixsec.com. So now we can do some memory study. We collect apps from 1.3 million Android apps and 140,000 iOS apps, remove the duplicates. And from the Apple Store, we got 10,000 apps, and Google Play is like 400,000 apps. In the end, we find on Android side, we got over 700 libraries with nearly 5,000 variations. It includes 117 libraries, potentially harmful. And it impacts about 7.88% apps. On iOS side, we got 46 from this 117, potentially harmful when mapped. And from them, there's 23 libraries are potentially harmful. So we try to look back to the markets and to see how many apps are potentially harmful. So on Apple Store, we found about nearly 3,000 potentially harmful apps. So the ratio is about 2.94%. And on other markets, like the jailbreak market, the ratio is higher, like 5 to 17%. We also find 27 potentially harmful libraries have over $10 million. It impacts lots of users. And over half of them, of this potentially harmful app, were actually uploaded after 2014. And over 1,000 apps have been on the store for quite a long time. It's 24 months. So we want to look into the code and to find what kind of behavior does this potentially harmful app that have. First, it take pictures and send it out, or record, play voice, or download apps and install, or steal private information such as the user's account, location, and some code related to a jailbreak or keychain. Here's an example on iOS side. It's installed one IPA file. The file is in an enterprise certificate, and it's used a private API to install, like here, in a red font. We also found that some library that has many potentially harmful behavior inside it. For example, here AdWall can use camera, record audio, and do some location and send it out, and has some others behavior inside. So the next question is, we want to understand how do potentially harmful libraries spread. So we do this on Android side. We use a normal version, it's clean version. And we use its variants, the potentially harmful library, and we compare it and do a diff on it. So we find the different code, and we disassemble the diff bytecode into Java source code and search the source code online. Finally, we find that it is on GitHub. That means some attackers repackage this library and put it online, and for others to download it. This is one way to spread potentially harmful library. The other one is library embedding. A careful developer might use a library from its official website, hoping that it is clean. However, sometimes the library has been contaminated. So this careful developer may use the potentially harmful library inside his app. So on iOS side, it's similar, and repackaged library are on the Apple platform. The same library tend to contain more suspicious behavior on third-party markets. We also find some special behaviors of this potentially harmful library, like evasion. The potentially harmful library do not call the API, which pop up a window for user approval. Only read the last retrieved location data from the host in background. So it's avoid to pop up window for users notation. And if a host app does not have the permission, then nothing will happen. The behavior also exists matched on iOS side. So here's a conclusion. We report a systematic study on mobile PHA library across Android and iOS platform. We run the methodology on 1.3 million Android apps and 140,000 iOS apps, and discovered many potentially harmful libraries. We found evidence that library contamination could be an important channel for propagating potentially harmful code. OK, so that's all. Thank you.
So do we have questions for the speaker? Okay, I have a question. So I found it interesting that you found strings were the main or the best way of identifying a library. And in the paper, there's a nice table that shows the different types of strings, and you can definitely see how these could be unique identifiers. It wasn't clear to me, so did you do any filtering to get rid of strings that might be common? And do you weight the strings differently? Do you try to identify what types they are? Like, are they URLs or code snippets? Like,
yes.
Tell me a bit more about that.
Yeah, we really need some threshold to do this, because there are some strings that's very common, just like you said, and in different classes. So both in Android and iOS, and in different classes, that should be matched. So in this way, first we try to find what kind of string that can be matched, like we conclude in several categories, just like we mentioned. And the secondary, we use a threshold. If two classes, we found that it shared the number of shared string beyond the threshold, we think that it's matched. Otherwise, yeah, we do not think it's matched. So yeah, I hope this answers your question.
I see. Okay.
Thanks.
Oh, we do have a question.
So it's a great talk.
Thank you.
This is Don from Qualcomm. So quick question is, I see in the paper you're trying to identify the harmful library by matching the strings. So I'm wondering, does like a control flow graph or data flow graph, this kind of graph can be useful here? So
yeah, it's a good question. Interesting. Yeah, we try to find, like, just like you said, a control flow graph. However, in real situation, the control graph may be so diverse, because the apps from the Android side and the apps from the iOS side are usually developed from individual developers. They're different groups. Although they are in the same company, but they're different groups. So people could design their approach, design their methods in different ways. So the two methods within the Android part and the iOS part are quite different. Usually we cannot find a matched like in method level. So we try to find it in class level. This is because they have a general high-level design, so they design the class to be like similar, and especially when the code need to communicate with outside, like with a server. So these protocols are the same. But for this development of these two individual libraries, they are not the same. Yeah, but we try to find it. So yeah, I failed. Cannot find it. So we use this commerce string to do this match, and we found it works. Okay, thanks.
Another quick question is, I noticed like sometimes some malware, they're actually using encryption to encrypt their string, so you cannot detect them easily. So do you find the problem during this research?
Yeah, sometimes they use the encrypted string. Yeah, so we can divide it into two parts. So we really found some common encrypted string in both Android side and iOS side. So that means this part may be related to like outside to the server. So this common string could be used for this map. On the other side, in if the app do something to conceal his code, like only on one part to conceal the code, so we cannot find it. Because we want to make estimation of the lower bound of this potentially harmful library in this market. So yeah, if they want to evade our detection, so our approach is not a detection approach. It's only to try to find the potential harmful library across the market. So we cannot find it. Okay.
Thank you a lot.
Thank you.
This will be the last question.
Hi, I'm Chen from Georgia Tech. Thanks for the interesting paper. So I have one question. From what I understand, most of the harmful apps use the private APIs to do the attack or like harm the users. From what I know, Apple strictly forbids the use of private APIs. Why do you think they fail to detect such use of APIs?
Oh, yeah, we use a dictionary for this mapping. If they have, it's just like you said, if they use private API to do some potentially harmful things, on Android side, if they still have this behavior, and we could map this. Because on iOS side, we do this map to map the private API to like its category, and we manually analyze this private API. So if it really exists on this iOS side, we can map it from this Android side to its iOS side. So, did that answer your question?
Okay, thanks.
Thank you.
Let's thank the speaker.
And